And we're live, so welcome back. We had a number of questions that were sent in about integration, so I'm going to run through a bunch of your response related to integration. First one involves some volume by cross-sections. For all the ones that we go through today, if they're questions 1 or 2, then they are with a calculator. If they're questions 3 through 6, then they are without a calculator. So first one's no calculator. I've got two functions, f and g. F is the square root of x, and g is 6 minus x, given in the picture up here. R is the region bounded by the x-axis in the graphs of f and g. So first part they want us to do is find the area of R. What do I have to do to get the region between these three curves, really?
Integrate from 0 to 4 and then add the triangle.
Perfect. So I'm going to integrate from 0 to 4 of f of x in terms of x. And then I'm going to add our integral from 4 to 6 of g of x, which you're right is just a triangle. So let's get the easy part out of the way first. What's the area of that triangle?
2.
Okay. So I'm going to throw that over here. And then I need to integrate our square root of x from 0 to 4. Square root of x is the same thing as x to the 1/2 power. So what will happen if I integrate x to the 1/2 power?
X to the 1.5 power and times 1.5.
So this will be x to the 3/2 power, you're right, but when I integrate it, add 1 to the power, then divide by the new power. So if I divide by 3/2, what will I have left?
2 over 3.
2 over 3, perfect. 2 over 3. Okay, and I did have bounds there, from 0 to 4. So I'll have to plug in those bounds. Okay, so if I plug in 4 right now, this would be 2 times the square root of 4, which is 2, to the 3rd power, which is 8, times 2, which is 16, divided by 3. So I've got 16 over 3 plus, I'm going to convert this to 6 over 3. Should give us 22 over 3 for our total area. Any questions on what we did for part A?
No.
Alright. For part B, I think I'm going to draw on this. So we're told that region R is the base of a solid. For every y value from 0 to 2, the cross-section of the solid taken perpendicular to the y-axis is a rectangle whose base is an R but whose height is 2y. I want to write an integral expression that gives the volume of the solid, but we don't have to evaluate it. So I'm going to draw a picture really quick. If I'm perpendicular to the y-axis, then that means we're going to look something like this. So I've got an infinitely small dy here of a cross-section that is perpendicular to the y-axis. And that rectangle pops out of the page to look something like this. Nope, that wasn't a terribly good rectangle, but you get the idea. So, what will the length of this side be? Our side that's in the xy plane.
G of x minus f of x.
Close. G of x and f of x are y values.
The inverse of them.
Inverse of them. Not the inverse, no. Okay, I need to be looking at x values, not y values. So this is going to be my x value for g. I'm going to call that x2. Minus my x value for f, which I'll call x1. What is x2?
Whenever they are have the same y value.
They're only going to have the same y value for both the first function and the second function when x is 4. This x2 minus x1 is this whole line here in yellow. My change in x should give me the length of the side of this rectangle that's in the xy plane, so within that region R. I want to know what's an equation for the x value of g of x?
Y minus 6.
Minus 6, oops. Sorry, I've actually copied this wrong, but this wasn't x minus 6. G of x is 6 minus x. That's my mistake, not yours. 6 minus x. Okay, then what is my x value then?
6 minus y.
Okay, cool. Okay, I'm going to call this x2 to match what I had earlier. Okay, then I'm also going to do the same thing for my f of x. So f of x was equal to square root x, or y is equal to root x. So if I solve for x, what do I get?
Y squared.
Y squared. Okay, so for this side that I had here in yellow, that side is actually 6 minus y minus y squared. Okay, any questions on what we did there?
No.
Okay, I'm also told that we had a height of the rectangle popping out of the page of 2y. So this height on this side is 2y. Okay, so I'm going to scroll down and we'll redraw this rectangle really quick with the side lengths that we just got. So this is something like this, where we had six minus y squared in the xy plane, 2y popping up as a height, and an infinitely small change in y that was the depth of this box. Okay. I think I would normally take all of this that we just created. Oh, I don't know if I can move it though. And put that as part of our work. Let's see if I can just copy that down. Yeah. Okay, so we solve for both of our x values. We needed to create an integral expression that gave the volume of that solid. So how can I get the volume of this solid?
Integrate this expression from y equals 0 to y equals 2.
Okay, I'm going to integrate from 0 to 2. What's my expression?
Y minus 6 minus x squared, y squared.
I had 6 minus y, but
Oh, 6 minus y.
Okay, 6 minus y
Minus
minus y
x,
squared.
y squared.
So that's one side length. What else do I need?
Oh, times the whole inside integral to 2y.
Okay, times 2y. So that's my base times height. And I need to make it a volume, so I need one more dimension.
Dy.
Times dy. Okay, sorry, you might have said that already, kind of cut out. So if I multiply the base times width times height, then I should get a volume. And that should look good. They did say we don't have to evaluate it, so we can stop there. Okay, and we're also told there is a point P on the graph of f, at which the line tangent to f is perpendicular to the graph of G. They want us to find the point P. What's the first thing I need to know if I want to find the point on f that would be perpendicular to G?
Find the derivative.
Derivative of which one first?
For f of x.
Okay. So I'll do derivative of f first. I guess I'll do this in 2 steps. So our f of x was x to the 1/2 power. What happens when I derive?
1/2 x to the negative 1/2 power.
Okay, or 1/2 root x. I actually need the derivative of g as well, because I need to figure out where this is going to be perpendicular. So, what is g prime at x?
Negative 1.
Negative 1, okay. I'm looking for the graph that is perpendicular to g. So if g prime is negative 1, what does the slope of our tangent line need to be?
Positive 1.
Positive 1, perfect. So a line perpendicular to G will have a slope of the opposite reciprocal, which is 1. Okay, so what do we need to do in order to figure out what the x value will be for the point where f of x is going to have a slope of 1?
Set 1 equals 1/2 root x.
Perfect. So 1 equals f prime of x, or 1 is equal to 1/2 root x. So what is x equal to?
1/4.
Perfect. Okay, so x is 1/4. That could have been plus or minus 1/4, except we're on the interval from 0 to 4. So I know that has to be positive 1/4. Okay, they said find the coordinates of P. So I've got an x value. What else do I need in order to get my y value?
Put the 1/4 back into f of x.
Okay, so I'm going to take f of 1/4. F of x was the square root of x. So this should be the square root of 1/4. What's the square root of 1/4?
1/2.
Okay, so what's our final answer?
1/4, 1/2. Oh yeah.
Perfect. Okay, I'm gonna box these answers in really quick. And we're good to go. Any questions on the first one? Let me zoom out.
No.
Okay, cool. I didn't realize I made different colors there. Okay. Let's zoom back in and we'll get to the next one. Okay, so this is same year but question 1, so we will have a calculator for this one. So we throw that up here while we're at it. So we're told that there is a cylindrical can with a radius of 10 millimeters used to measure the rainfall in Stormville. Initially the can is empty, and rain enters the can during a 60-day period. The height of the water in the can is modeled by this function s. S of t is measured in millimeters, t is measured in days from 0 to 60. The rate at which the height of water is rising in the can is given as s prime of t is 2 sine 0.03t plus 1.5. First thing they want to know is, what is the height of the water in the can at the end of this 60-day period? What do I have to do?
Integrate from 0 to 60 of s prime.
Okay. Normally I would have to worry about a start point as well. So I would do s at 60 is equal to s at 0 plus the integral from 0 to 60 of s prime t dt, which is... it is the same thing that you gave me for this one though, because we were told the can is initially empty. Okay, I'm gonna put this back inside the lines, but... so that's what we're gonna do in the calculator. To make this easier on ourselves for later, I'm going to actually store this value in our calculator so that I can use it again. So if you hit y equals, then we can type in our function there. So this is 2 times the sine of 0.03t plus 1.5. Okay, then I want to integrate from 0 to 60, so I'm going to break out and hit math. 9th option is our integral of variables, y variables, function, y1. So that's everything we just typed. I'm going to integrate y1 in terms of x from 0 to 60. Okay, so s at 60 is equal to 171.813. What are our units?
Millimeter.
Perfect. So this is the height of the water in the can. For part B, we're looking for the average rate of change in the water, or average rate of change in the height, that is, of water in the can over the 60-day period. So if I want average rate of change, what should our formula for the average rate of change of the height be?
S prime.
Okay, I'm going to make an estimate for s prime, but we're not looking for the derivative, I'm looking for the average rate of change. So what's the algebra form of the slope?
From start to end, which is the integral divided by 60.
Okay, you're right. I'm going to write this as s at 60 minus s at 0. So that's my change in y over my change in x, 60 minus 0, should be equal to my average rate of change of s. Your method would have worked. We could integrate this and then divide by 60 to get my average using average value formula. And this is the same math, but we've already integrated from 0 to 60, so we already know this number. And I've actually still got it in my calculator up here, so we know that s at 0 is 0. So this is 171.813. 473 divided by 60. Or 2.863. I'm going to round that to 2.864. What are our units?
Millimeter per days.
Perfect. Millimeter per day. Okay, part C. Assuming that there's no evaporation, at what rate is the volume of water in the can changing on the 7th day? And then indicate the units of measure. So first, what's our general form for the volume of this can? Or volume of water in the can?
Um, the integral of s.
If I integrate s, it's going to give me the height. So if I integrate s, I'll get s of t. What else do I need besides the height in order to get the volume?
Oh, the base.
Okay, so I need the area of the base. This is a cylinder. So what should the area be if the radius is 10 millimeters?
100 pi milliliter squared.
Perfect. So I've got 100 pi is my base. Will that base change as I go down the cylinder?
No.
Okay, the area of that base does not change as we go down the cylinder. So because it's a constant, our volume is really just this constant 100 pi times our s of t. What will happen when I derive our volume?
Into s prime, 100 pi.
Okay, 100 pi times s prime at t dt. Okay. So I wanted to find the rate at which the volume is changing at the time t equals 7. So what do I have to do here?
Oh, plug in 7 and what is the dt going to be?
Actually 1, because we just derived t in terms of time. So this is really dt over dt, which is 1. I'm just throwing it in there because of chain rule.
Oh, okay.
Okay, so I've got 100 pi times s prime at 7, so I'm going to jump into my calculator again. Right now, on our y equals... Oh, can't click with pen. On our y equals, I already have this as the rate of change. So this is s prime at t right now. So I'm just going to plug in our value for 7. I think I'll do that with the table. Maybe calculate value. So when x is 7, our value is 1.916. So I could say something like... Actually, I'm going to quit out here and store that. X store as a. Okay, so whenever I... Uh-oh. That's not my y value. Oops. Do this. Okay, so there's our value, and I'm going to multiply that by 100 pi. To get our v prime at 7. So that was 602.218. What are my units?
Cubic millimeter per day.
Perfect. So cubic millimeters per day is my change in volume over time.
For the calculator, it's the 7 is supposed to be a degree, right?
Sorry, say that one more time.
So when we plug the 7 into the calculator, is it supposed to be in degree or radian?
The entire AP exam is in radians, so you should never be in degrees. By default, if you reset your RAM, your calculator will be in radians. If it's not, make sure that you're in radians before the test.
Oh, got it.
Okay. Part D, during the 60-day period, Rain on Monsoon Mountain accumulates in a can identical to the one in Stormville. We're told that the height of the water in the can on Monsoon Mountain is modeled by the function m. M of t is 1 over 400 times 3t cubed minus 30t squared plus 330t. Our height is measured in millimeters, t is measured in days on 0 to 60. We have a new function dt, which is equal to our change in m minus change in s. I want to apply the intermediate value theorem to our new function b on the interval from 0 to 60 to justify that there is some time t from 0 to 60 at which the heights of the water in the two cans are changing at the same rate. If they were changing at the same rate, what would dt have to be equal to?
Zero.
Cool. So I'm going to write that as my first step. If m prime t equals s prime t, then d of t equals 0. Okay, so what is the intermediate value theorem?
So if a function is differentiable, then between 2 points, there's the point that is the same slope as the secant line.
Okay, so that's actually mean value theorem. Intermediate value theorem says as long as our function is continuous, we don't have to be differentiable. We will pass through all of the y values between a and b.
Oh yeah.
Okay, so both of these functions are polynomials. Sorry. S prime at t is not a polynomial, it's a sine function. I got one polynomial and I've got a sine function. Are both of these functions continuous from 0 to 60?
Yes.
Yes. Okay. So I do need to write that actually. That'll be the first part of my conclusion, as both functions are continuous. Okay, and we'll keep going with that in a second. Both functions are continuous. The next thing I need to do is prove that m prime t will equal s prime t at some point on this interval. So I'm going to take a look at what our starting value is and our ending value is. If one of them is positive and one of them is negative, then I will have to prove through 0 in order to get from the first one to the second one. So that means I need to know what m prime at 0 is. So taking a look at our function, I've got this crazy polynomial, but if I derive it, what's going to be left?
Um, 1 over 400 9t squared minus 60t plus 330.
Perfect. Let me go ahead and write that over here somewhere. So m prime at t is equal to 9t squared. I'll do 1 over 400 times 9t squared minus 60t plus 330. Okay, so what is m prime at 0?
Um, 33 over 40.
Okay, 33 over 40. Actually, I probably don't need to do this by hand. This is with a calculator. Okay, I'm going to backtrack. I'm going to skip and we'll do d at 0 in the calculator. And to do that, I'm going to plug in our new function that you just gave me for m prime at t. So this is 1 over 400 times 9t squared minus 60t plus 330. And then I'm going to create a new y3 that is equal to y1 minus y2. So that's variables, y variables function y1. Oop, it's actually s of t. Sorry. Variables, y variables function y2 minus y1. Okay, so I've got m prime t minus s prime t is now my y3. So now I can break out and get that x value at 0. So variables, y variables function y3 parentheses 0. So I'm plugging 0 into y3. When I hit enter, my x value is negative 0.675. Okay, then I'm also going to test my endpoint. So that's variables, y variables function y3 at the point 60 is positive 69.377. Okay, as both functions are continuous, the intermediate value theorem guarantees that there will be a point on 0 is less than x is less than 60, where d of x is equal to 0. As we must pass through all d of x from a negative d of x to a positive d of x. May have been a little bit wordier than what I needed, but any questions on what we did?
No.
Okay. Because this is with a calculator, we probably didn't need to actually write our m prime t. As long as we got our, we tested 2 points to prove that our y values changed from negative to positive values, and then mentioned that the function was continuous, we've got enough information to prove that IVT will guarantee that point. So really, the only information I think we needed for this, I'm going to highlight in yellow, was this part. So finding our start point, this part, finding our endpoint, mentioning that we are continuous, and then guaranteeing that there will be a point where d is 0.
For the AB test, will we ever have to explain why a function is continuous?
You may have to. We don't have to here, because they asked us to justify the IVT, not to justify continuity, but they could give you a piecewise function and ask you to justify why this piecewise function is or is not continuous. And in that case, you would have to prove that the general limit is equal to the y value when you actually plug that point in. So that would prove continuity, or if any of that's not true, then it would not prove continuity. So if your one-sided limits do not match, you're not continuous, or if you have a general limit, but that doesn't equal what happens when you plug in the point, then you're not continuous. So they may ask you to do it, but they didn't ask us to here.
Got it.
Cool. Any questions on anything else from this one?
No.
Okay. I'm going to decide whether or not to skip really quick. So we're a little shorter on time than I'd hoped. Let's see, this one is question 6. I am going to skip this one, so I'm going to skip down to 2011-5, so we can get at least one separable differential equation in here today. I might come back to this next one for the next session. Okay, so question 5, 2011, this one is without a calculator, so I'll go ahead and close this. We're told that at the beginning of 2010, a landfill contained 1,400 tons of solid waste. The increasing function W models the total amount of solid waste stored at the landfill. Planners estimate that W will satisfy this differential equation. Our change in W over change in time is equal to 1/25th of W minus 300 for the next 20 years. W is measured in tons, T is measured in years for the start of 2010. For part A, I want to use the line tangent to the graph of W at T equals 0 to estimate the amount of solid waste that the landfill will contain at the end of the first 3 months of 2010, so at the time T equals 1/4. What information do I need to graph a tangent line?
The slope.
Okay, I need the slope, so we'll go ahead and get the slope first. Our slope will be what happens when I plug in our W into this equation. So I can say I'm highlighting, our slope dW over dt. At the time T equals 0, since I'm going to use our tangent line at T is 0 for our estimate, should be equal to, what was my W at T equals 0?
For 1400.
Okay, 1400, so this is 1400 minus 300. So our change in W over change in time, or our slope, is going to be equal to 1100 divided by 25. What is 1100 divided by 25?
44.
44, perfect. So dW over dt is equal to 44 at 0. So that gives us the slope we need. So then I need the equation for our tangent lines. That's y minus our y value should be equal to our slope times x minus our x value. Okay, so that's our tangent line. And I'm going to use that to estimate what happens. Uh-oh, made a mistake there. Our time is actually 0 for this. Okay, but I'm going to use that to estimate our new y value when our time is t equals 1/4. Okay, so what do I have to do with this?
Plug in 1/4.
Okay, plug in 1/4. So I've got y minus 1400 should be equal to 44 times 1/4. What is 44 times 1/4?
11.
11. What is 11 plus 1400?
1411.
Okay. What are my units?
Tons.
Okay. Tons of solid waste. Okay. Second part, I want to figure out what the derivative of this would be in terms of w, and then use our derivative to determine whether our answer in the first part was an underestimate or an overestimate. So let's do the first part first. I need to get the second derivative of this function, so what happens when I derive right now?
The second derivative.
Okay, what is the second derivative?
1 over 25.
1 over 25 chain rule times what?
dw.
Okay, dw over dt. We already know what dw over dt is, so I'm going to resub for dw over dt. So this is the second derivative of w in terms of time is equal to 1 over 25 times dw over dt, which is 1 over 25 w minus 300. Or 1 over 25 times 1 over 25 is 1 over what?
225. 625.
Cool. 625 times w minus 300. Okay, so we've got our second derivative. And I need to use this to figure out whether we were underestimating or overestimating with our tangent line. So at the point where w is equal to 1400, so that was where we started, were we concave up or concave down?
Concave down.
Okay, when our t was 0, what was my w equal to?
Oh, 1400.
1400, okay, so this is really 1 over 65 times 1400 minus 300. So at the t equals 0, this is 1100 over 625. I'm going to leave it like that for now. So that means we were concave up. And then, do we know if it was increasing or decreasing? I can put that in, but... Okay, we were increasing the entire time. So on the interval from t equals 0 to t equals 1/4, we were increasing. Increases on 0 is less than x is less than 1/4. So do you think we overestimated or underestimated with our tangent line?
Underestimated.
Underestimated, perfect. So our function looks something like this in red, but our estimate would have looked something like this in blue, because we use the same slope that we had at the original point to keep going and make our estimate. So I could say, therefore, our tangent line approximation underestimated the waist. Okay, any questions on the first part?
No.
So, okay. Last part, part C. I want to find the particular solution to the differential equation that they gave us, dw over dt, with the initial condition w at 0 is 1400. I'm going to blow this up so we have a lot more room to work, and maybe change the color so I know this is a separate question. So we'll do this in blue. Okay, so we were told dw over dt is equal to 1/25th w minus 300. And w at 0 is equal to 1400. Okay, what's my first step that I need to do for this separable differential equation?
Differentiate both sides.
My goal is to solve for w. Right now I have a dw over dt, so I can't differentiate.
Oh, integrate both sides.
Okay, I want to integrate both sides, but I do have a problem there as well. On the left side I have both w's and t's. On the right side I only have w's. So before I can integrate, what do I need to do?
Oh, times dt to both sides.
Okay, I'm going to multiply by dt, but that'll still give me w's and t's on the right side, so what else do I need to do? How could I move all of the w's to the left and all of the t's to the right?
Oh, divide dw both sides.
Okay, so I'm gonna leave w on the left side. That means I have to divide by what?
Oh, 1/25 times w minus 300.
Okay, I could. I'm actually gonna move just the w minus 300 because that saves me from having that fraction inside a fraction nonsense. And keeping this constant here, since I just have dt on this side, is going to be fairly easy to integrate. Okay, what happens when I integrate our left side? What? Sorry about that. That threw me way off into the last question. Where are we? Okay, there we go. What happens if I integrate this left side?
ln w minus 300 times times negative 1.
Okay, actually don't need the negative 1, because that w is positive. So I would have a plus c, but I'm also going to have a plus c on the opposite side. And since they're from different integrals, they're not the same c. So when I combine them, these will end up combining into the same constant. So I'm just going to leave my plus c on the right hand side instead of writing them on both sides. What happens if I integrate 1/25 dt?
1/25.
1/25
Times t.
times t. Okay, so I'm going to write t over 25 plus c. Okay, this is probably a good place to solve for c, and I say that because looking at our initial condition, if I plug in t equals 0 right now, then the only thing I'll have on the right side is c. So I don't have to solve for c right here. I could wait until the end when I solve for w. But it looks like a good place to throw it in right now. So I think I'm going to do that. So I'll solve for c first. And then we'll continue after that. So if I solve for c, I'm going to plug in t equals 0, and w equals 1400. So this will be the natural log of 1100 is equal to 0 over 25 plus c. So c is the natural log of 1100. Okay, so if I continue, this will be the natural log of w minus 300 is equal to... Okay?
Yes.
Okay, is equal to t over 25 plus natural log of 1100. Okay, what do I do from here?
Separate out w.
Okay, my goal is to separate out w. What do I need to do to both sides in order to get rid of that natural log?
Have e as the base and each part as the power.
Perfect. Okay, so if I do that, this will become w minus 300 should be equal to e to the t over 25 plus natural log of 1100 all in the power. If I'm adding with the same base, how could I rewrite that?
Times.
Okay, I should be multiplying with the same... if I'm adding in my exponent, I should be multiplying with the same base. So this is really e to the t over 25 times e to the ln 1100. What is e to the ln 1100?
1100.
1100, perfect. So this is w minus 300 is equal to 1100 e to the t over 25, or w is equal to 1100 e to the t over 25 plus 300. That should be our answer. Do we have a domain for this?
Do we still need the absolute value?
Do we still need the absolute value? Let's scroll out so I can see for a second. Okay. I don't need our absolute value right now because I don't have any natural logs left.
But what happened if w is... Oh, never mind, it's in terms of t.
Okay. Do we have a domain?
More than 0.
Okay, we've got to be more than 0. It goes for the next 20 years. Okay, so this is, that function we used was only true for 20 years. So I could say for 0 is less than t, oops, is less than 20. Okay, and that should be good. Any questions on anything from this one?
No.
Okay, sorry about the tech hiccups there. Thanks again for coming. I'm going to keep going tomorrow with some of the ones that we didn't get to. So we'll see integration with piecewise functions and some general integration stuff that people asked for. So integration with some composite functions and definite integration.
Okay.